Let's now have a hands-on experience with using TensorFlow with convolutional neural network to do image classification. So this is a Google Colab notebook. We will do image classification with CNN. We start with importing some of the TensorFlow modules, and then we will train for 32 epochs and use batch size of 32. We are loading the data here by using keras datasets.cfr10. Then we want to standardize the dataset, so we compute the mean and the standard deviation, and note that we always compute the mean of the training examples, and we use the mean of the training example and the standard deviation for both the train image and for the test image, so that we can get more accurate results. Then here we are encoding the training labels as one hot encoding by using two categorical method in the library, and then the output will be 10 classes. This is for the training labels and for the test labels. Let's now look at how we can define our network. So it's a sequential network, as before, where we stacked a number of layers on top of each other. It consists of two convolutional layers. This is the first convolution layer, this is the second one, and the output, which is a fully connected layer. As we can see here, we didn't use any flattened layer at the beginning of the network because previously in the fully connected layer, we needed to have the flattened layer because the fully connected layer assumed that the input is one-dimensional array. But in the convolution layer, it assumes that we have a 3D array, which is the input image. So it's a two-dimensional 32 by 32 plus the number of colored channels that makes it 3. This first convolution layer, we say that we want 64 output channels. We want a kernel size of 5 by 5 and a stride of 2 by 2. We use ReLU as the activation function, and we use padding as same. With padding equals to same, if we had a stride of 1 by 1, then the output dimension would be the same as the input dimension. But given that we have a stride 2 by 2, it means that the output dimension will be exactly half of the input dimension. So with an input shape 32 by 32 by 3, the output will now be 16 by 16, and then by the number of channels, which are 64. So this is the input shape, 32 by 32 by 3. After doing this, padding same and stride 2 by 2, the output will be 16 by 16 and the number of channels, which is 64. And we use the normal initialization for the weights, and we set the bias to be 0. The second layer of the convolutional layer, we also use 64 channels. We have a smaller kernel size, 3 by 3, and the stride is 2 by 2. And we use also ReLU for the activation function and the padding to be same, and initialization, and we zero the bias weight. Now we go from a convolutional layer to a fully connected layer. And there we have a mismatch in dimensions because we have a 3D structure from the convolutional layer and assuming a 1D dimension for the fully connected layer. So here we need to use this flattened layer. And then this is the output layer, which has 10 neurons, and the activation function is softmax, and we use chlorot uniform for the weight initialization, but for the bias weights, we set it to be 0. And then we use softmax. We want to use the categorical cross entropy as a loss function, and we use the Adam optimizer. And then, as we use a softmax, we want to use the categorical cross entropy as the loss function, and we use Adam as the optimizer, and we use the accuracy for the metrics, and then we will print out the summary of the model. Then the training of the network, we call the fit function with train images and train labels. With the validation data is the test images and the test labels, and the epoch and the batch size. Let's see the output here. We see that after 32 epochs, that the accuracy on the training is pretty good. It's about 95%. However, if you look at the validation accuracy, it is about 61%. So this is a clear indication of overfitting, where we see that it learns the training dataset but does less well on the test set. This is a modified version of the CNN to mitigate this overfitting problem. I'm calling here the dropout and the max pooling 2D, because I am using it here in the creation of the network. So this is the first layer of the convolutional layer, and then the dropout, then convolutional layer, then dropout, then convolutional layer, dropout, convolutional layer. So here I have 1, 2, 3, 4 convolutional layer, and I'm using also here max pooling. And here the same, we use the flatten, because we are now going to the fully connected layer. We have here 1, and then drop out, then another fully connected layer, and then another fully connected layer. So we have 4 convolution layers and 3 fully connected layers, and we use ReLU neurons for all convolutional layer and the fully connected layers, except for the last one, where we do the softmax. And then the rest of the things are the same as well. We print out the summary of the network, and we see here the number of trainable parameters for each layer. And then we can see here now the process of training. So after the process has finished, we can see that the accuracy now for the training data is about 75%, and for the validation, it is about 76%. So by having the more and this deeper network with more layers, and by adding the dropout regularization, not only did we manage to get the overfitting under control, but we also got the validation accuracy to improve significantly.